The deeper a neural network becomes, the more the sheer mathematical weight of its own data begins to crush it. Modern large language models rely on standard residual connections. These act as gradient highways, allowing data to pass forward through hundreds of layers via uniform, fixed-weight addition. This is the standard residual formula. Unrolling it reveals a flaw. Every layer receives the identical sum of prior outputs. Under prenorm, this accumulation creates strict O of L growth. The hidden state swells, suffocating the original token embedding at the bottom. Researchers call this prenorm dilution. By the time data reaches the deepest network layers, early layer information, the actual context, is entirely diluted and inaccessible. The immediate consequence is highly inefficient compute. To exert influence over this swollen residual stream, deeper layers must produce increasingly large outputs. Prenorm allows models to train at extreme depths, but it structurally starves the network's end of the foundational context it requires to operate. The Kimi team proposed a theoretical pivot to solve this. Treat the vertical depth of a network exactly like transformers treat horizontal sequence time. Standard residuals bottleneck data across network depth through a single central pipe. Full attention residuals eliminates this, replacing it with softmax attention across depth. Each layer uses a learned query to scan tasked outputs, selectively retrieving exact historical context. To prevent the magnitude blowouts that plague standard prenorm, an internal RMS norm function regulates the keys before the softmax is applied. In theory, this introduces almost zero overhead. Standard backpropagation already requires the system to save these past layer activations in memory. Depthwise softmax attention shatters the uniform compression bottleneck. Deep layers can now dynamically retrieve the precise historical data they require. Theoretical elegance means nothing if it crashes GPU clusters during distributed training. Training massive state-of-the-art models requires pipeline parallelism. The network must be split across multiple physical GPU stages. Look at this simplified pipeline. In a standard residual architecture, passing data between these stages is highly efficient. The system only transfers a single fixed-size hidden state across the boundary. The fatal flaw of full attenres at scale is that the next pipeline stage needs to query the past. That requires explicitly transmitting every single individual layer output across the stage boundary. Mathematically, this triggers an OLD communication and memory overhead explosion. The traffic scales linearly with depth, choking the interconnects. Without a severe systems-level engineering workaround, the cross-layer access required to make full attenres function makes it impossible to scale. To bridge this gap between theoretical depth attention and hardware reality, the team engineered block attention residuals. The core modification is simple, partitioning the entire vertical network into a fixed number of blocks, typically 8. Within each block, the layers sum together normally, exactly like standard residuals. At the boundary, they output a single compressed summary vector. Now, when a deep layer sends out a query, it only performs softmax attention over that handful of block summaries. This plummets the memory requirements from O of LD down to a manageable O of ND. This solves the memory issue, but it leaves a second problem, mitigating the redundant transfer of these block summaries across virtual pipeline stages. This grid maps the solution, tracking data across 4 physical GPU ranks and multiple virtual stages. Instead of sending the full history every time, the physical ranks cache previously received blocks in local memory. When shifting to a new virtual stage, the system transmits only the incremental new blocks. During inference, merging these parallel block summaries with the sequential local layers is handled by a 2-phase online softmax strategy, keeping the math strictly equivalent. By compressing network depth into blocks and caching them across pipeline stages, attention residuals scales directly into 48 billion parameter models as a drop-in replacement, with a negligible penalty to latency. The infrastructure supports the scale. The empirical data proves it actually tames the chaotic signals inside the network. We can see this clearly by analyzing the training dynamics of the 48 billion parameter model, trained on 1.4 trillion tokens. This graph tracks output magnitude of a baseline model across transformer blocks. As expected, it suffers severe dilution, relentlessly increasing the deeper the network gets. Overlaying the block attend res data shows the new architecture confines this growth into a strict, bounded sawtooth pattern. The sharp drops in the graph occur because the selective aggregation explicitly resets the magnitude accumulation at every single block boundary. A second chart tracking gradient magnitudes reveals the knock-on effect. The baseline spikes wildly at the early blocks, struggling to pass data back. The block attend res model draws a perfectly flat horizontal line across all layers. Mechanically bounding the network state directly cures prenorm dilution. The early layers receive the exact same gradient equity as the deep layers. The architecture restricts growth and balances gradients. But do the deep layers actually utilize this new ability to reach backwards for context? This attention heat map plots deep layers on the y-axis against historical block sources on the x-axis. The bright diagonal proves layers still rely on immediate predecessors, fulfilling their residual function. But notice the persistent off-diagonal weights locking on to source 0 on the far left. This is visual proof of learned skip connections. Deep layers are actively bypassing the standard residual stream to dynamically pull raw token embedding data from the very start of the network. This structural superiority maps directly to raw scaling performance. This graph plots validation loss against compute in pflops, showing a clear gap between the standard baseline and block attenres. At 5.6 pflops, block attenres matches the baseline loss while operating with a permanent 1.25x compute advantage. Transformers solved the sequence bottleneck by allowing any token to selectively retrieve any pass token. By applying that exact same mathematical logic to network depth, attention residuals rewrites how information survives deep inside massive language models.